January 21st, 1976, two supersonic planes take off, one from London, the other from Paris. Speed 1,350 miles per hour, twice the speed of sound.
The Concorde was an incredible aircraft, super gorgeous, well ahead of its time.
It took more than 30 years to develop, led by aeronautical engineer Sir James Hamilton, who famously designed the Concorde's delta wings, adding to the overall distinctive appearance of its tilted nose and long, ultra-thin body. But initial public awe quickly dissolved. When one of Air France's Concordes crashed shortly after takeoff in July 2000, it added one more thing to criticize to an already growing pool. Critics said the Concorde was too expensive, too elitist, and much too noisy.
It wasn't that the technology didn't work, it was that the economics didn't work. It was simply too expensive for enough people to afford to fly.
That's because fuel was pricey, and almost 22 hours of maintenance was required for every hour in the air. That maintenance also needed a specialized crew, in part because of the cooling mechanisms that managed the plane's high-speed temperatures. And then there was the boom. A thunder-like noise from breaking the sound barrier that could be heard on the ground. The noise caused many countries to ban the Concorde's overland routes altogether, meaning less money to be made. By the fall of 2003, Air France and British Airways had retired their Concorde fleets. 17 years later, we still don't have another Concorde. So what's the super holdup on supersonic planes? Well, companies are still solving the challenges the Concorde faced. Speed, fuel efficiency, and noise from the sonic boom. Boeing, Lockheed Martin, and Airbus are all at various stages of development to bring the supersonic passenger aircraft back. And the Federal Aviation Administration stated in 2008 that interest in supersonic aircraft technology has not disappeared. Today, companies are choosing one of two paths to go beyond the speed of sound: private planes or commercial airliners. Spike Aerospace is on the first path, private supersonic jets. Its design has reduced the sonic boom to the sound of a car door slamming.
You do that by changing the aerodynamics of the plane, the shape of the plane, the shape of the nose.
Its aircraft has a long pointy nose to help bounce the shockwave towards space instead of the ground, and its sleek windowless fuselage will help lower the cabin noise. Finally, Spike substantially updated Concorde's famous delta wing to a crank delta wing to control the pressure waves.
It's what's called a clean sheet design. We're not basing it on pre-existing model. We're basing it on knowledge about aircraft. It has to have a wing and engines, but otherwise the cabin can be done completely differently. How we shape the nose is different.
To deal with the Concorde's temperature issues, Spike built its aircraft with composite materials, lighter than aluminum and capable of tolerating higher temperatures. And instead of creating a new engine from scratch, Spike is simply modifying an existing engine, shaving 10 to 15 years of development and potentially billions of dollars. The catch? Spike plans on flying at a slower speed of 1,100 miles per hour. Still faster than the speed of sound, but slow enough to manage the temperature, sonic boom, and engine efficiency while cutting passengers' flight time by 50%. Spike hopes to eventually work its way up to larger commercial passenger planes, a path that Boom Supersonic is also on. The Denver company has been building smaller prototypes to test designs for a larger supersonic passenger jet. And since the company is initially focusing on overseas travel, the sonic boom isn't as big of an issue. Speed and efficiency are.
We've started from that same basic delta wing approach that Concorde had, and we've applied a lot of innovations. Through a combination of shaping the wing and optimizing the propulsion, we have a design for Overture that will be no louder than aircraft flying today.
The seamless angleless design is key. Not only is the fuselage made of carbon fiber composites that can tolerate higher temperatures, it also tapers by the wings.
There's a principle called area ruling, which basically says you want to keep the distribution of cross-sectional area continuous and smooth from tip to tail with the aircraft. And so where the wings stick out, the fuselage actually gets a little bit skinnier, and then it can be fatter after the wings. And so it's hard to find a straight line anywhere in the aircraft. It's like a smooth, flowing, continuous shape.
An updated engine is also in the works in order to improve propulsion and make the aircraft more fuel efficient. And Boom is aiming to make history next year by by test flying its supersonic jet XB-1, hopefully paving the way for overseas flights before tackling routes over land. But as of right now, no company working on supersonic aircrafts has conducted a test flight. In the meantime, companies are testing via traditional wind tunnel tests and modern computer flight simulators. Drawings are then rendered to design each and every part of the aircraft, measuring everything from noise, wind, and speed to temperature. And then companies can make adjustments for future tests.
Supersonic jets will be here by the mid-2020s. I expect that the general public will be able to fly a supersonic jet by the mid-2030s. This is really going to grow dramatically, and it's just the beginning of supersonic flight.
Only time will tell what our future of flight will look like and how fast we'll get there.